Kristen Atchison here, and we are going to finish up our problem on the room of the temperature affecting memory performance. We've previously hand calculated using this data our F ratio and determined our cutoff. We're able to reject the null and support the hypothesis and said that the temperature of the room made a difference in memory performance. We have our APA style F statement here. F212 is equal to 11.28. P is less than 0.01. And we also previously calculated effect size. So great. We have a difference. Yay! Somewhere in all that data, there's a difference. But the question is, where is that difference? And that's what the post-hocs are going to let us do. So we're going to both do a Tukey and a Scheffé and walk you through both of them. Okay, so here's our data. Again, we don't know where this difference is. We could say, is the difference here where we have a difference of 3? Is the difference here where we have a difference of 3? Or, well, we know it's not here because there's a difference of 0 between those two. So somewhere in these differences between either 50 or 70 or 70 or 90 or a combination of the two is where we're getting that significant difference. So first we're going to calculate Tukey's HSD. Remember, this gives us this single value that determines the minimum difference between these two to say that it's significant. We're going to look up Q. I've already looked it up for you. It's 3.77. We did that using K is equal to 3 and degrees of freedom within is equal to 12. I didn't specify a point value, so we're going to go 0.05. Again, this table is available for you on iCollege under week 6 homework. So if you need it, that's where I got it. And so let's calculate the math. We already know that our mean squared within that we calculated previously is equal to 1.33, and our n that we from before is 5. Now, again, this is little n, and so this is why Tukey has to be done with equal groups, because otherwise, which little n are you going to use, right? So the little n has to be the same in all 3 groups for this to work, okay? So we take 1.33 divided by 5, and we get 0.266. We'll take the square root of that, and we get 0.52. We'll multiply that by 3.77, and you might get a slight rounding error here if you're following along, but you get 1.94. Okay, so our HSD is 1.94. So anything greater than 1.94 means that it's a significant difference. Sorry there, that's a typo, 1.94. So anything that's the minimum difference, anything greater than that, we'll be able to say it's a significant difference. So here we have a difference of 3, check, that's a significant difference. Here we have a difference of 3, check, that's a significant difference. Here we have a difference of 0, big X, not a significant difference. So we're able to say that the difference between the 50 group and the 70 group and the 70 group and the 90 group is what was driving that omnibus effect, that we're getting differences significant differences between both of those groups. And again, Tukey lets you do that. Tukey lets you look at all of the pairs to see where that works. So the Scheffé test is different, and the Scheffé test actually requires a little bit more work, so it's going to take us a little bit more time, but it is the safest of all the tests. It does that because it really controls that experiment-wise alpha. It's going to do the best job of limiting that risk of making a type 1 error for the entire experiment, okay? So what we're going to need to do is we're going to need to recalculate mean square between with the 2 groups that we're interested in. Now the problem here is we can only really pick 2 groups. Every time you do a Scheffé test, you're going to up your experiment-wise alpha. So we're only going to pick 2 groups to do this with. Because they're equal, you really could have picked either one, but maybe something about our hypothesis says that it's really this 50 degrees versus 70 degree group where I think something's going on. Now, we've previously calculated that our T for group 1 is equal to 5, and our T for group 2 is equal to 20. And we've previously calculated that. We're going to need to recalculate that G only using these 2 groups now. So 5 plus 20 is equal to 25. So we have a new G. And these values are what's going to be used to recalculate that sums of square between treatment on this next slide. So again, we've we've already done that on this previous slide. So we have our T1, our T2, our G, and notice we also have a new N. It's big N, so it's the sum of all the groups, right? This big N is saying how many scores went into this G? Well, this G only has 10 scores in it, so our big N is 10, okay? So let's write this out. So we'll do 5 squared divided by 5, that's still the same, plus 20 squared divided by 5, minus 25 squared divided by 10. We'll do the math on that bad boy, so we get 25 over 5 plus 400 over 5 minus 625 over 10, which is equal to 25 plus 80 minus 62.5. So we're equal to 105 minus 62.5. We get a sums of squared between treatments of 42.5. Okay, so this is our new sums of squared between treatments for the subgroup 50 versus 70. Okay, so we've recalculated that for two groups, 50 versus 70, and this is our new sums of squared between treatments that we're going to use to calculate that Scheffé test. We still, however, need to turn it into our degrees of freedom, our mean squared between, okay? And how we do that is, again, using our degrees of freedom between. We're going to use that original between value where we had 3 groups minus 1 is equal to 2. We're not going to recalculate that. Again, this is part of why Scheffé is so safe, is because we're using this higher original value. We're holding ourselves to a higher statistical bar than if we were to recalculate this. Okay, so we already calculated our sums of squared between treatments as 42.5. We're using our previous degrees of freedom between, which is 2. We divide that out and we get 21.25. Oh, can't do that there. So we divide that out and we get 21.25. Obviously, making these videos is still a learning process for me. So that's our mean squared between, again, for this comparison group of the 50 degrees versus the 70 degrees, okay? So this is our new mean squared between. And again, by using this old degrees of freedom between, we're holding ourselves to a much higher standard than we would if we used our new one. Okay, so now we're going to calculate our F, A versus B. In this case, that's going to be 50 versus 70, right? Because those are the two groups that we looked at. Our new MS between was 21.25. Our old mean squared within, again, we're going to use this older value so that we're holding ourselves to this higher estimate, this better estimate of the within group variability, and we divide that out and we get 15.98. Our cutoff is 16.39, so we're still able to reject the null and say that there's a statistical difference between those groups. Again, by using this old mean squared within, that's the second reason that this is so safe, is because we're using that better estimate. Okay, thanks so much.